It's my pleasure to, so we're recording now. It's my pleasure to introduce Alessio Figalli from ETH Zurich. And today he'll discuss the complete classification of global solutions to the obstacle problem. I'm sure we're all very interested.
Okay, so thank you very much, Connor, for giving me the opportunity to talk at this online seminar. As I said, I'm very happy to see so many names of friends and face of friends here present. So yeah, we'll try to mimic a Blackboard talk by using the iPad. And I will talk about this recent result about complete classification to global solution to the obstacle problem. So I will start with an historical perspective on the question. So everything started back in 1678 with Newton. So Newton proved what's called the no gravity in the cavity theorem. So what is that? It just says the following. Probably many of you studied it in physics when they did physics. You know, you take a spherical cell. So this is a spherical, spherical shell. You just put charge on the shell, or let's say just you put uniform mass distribution on the shell, and you consider the potential generated by it. So let's say this is a ball of radius r, and then you take Laplacian of u equal the surface measure. So we are in R3, of course, physical dimension. So R3, you take the surface measure, the two-dimensional surface measure on the boundary of the ball of radius r. So this is just, either you can do either gravitational potential or electrostatic potential, depending if it doesn't matter. But what the theorem says is that if you take a uniform distribution on a shell, then there is no force inside. So the gradient of UR is identically zero inside the ball. So this uniform distribution doesn't exercise any force inside, no matter where you are, okay? So this is just saying spherical cells do not exert gravitational force. And this theorem of Newton was generalized roughly 100 plus years later, first by Laplace and slightly later by Eberle. So, it's the standard thing where there is a French and an English who do the similar things at the same time. What they did is they say that same is true for ellipsoids. So if you take an ellipsoid and put a uniform distribution on the ellipsoid, again, you don't have any gravitational force inside. I would like now to recast this in a slightly more robust way, because I would like then to take limits and make it like a more robust formulation. So instead of having surface measures, I would rather have, this charge distribution, or let's say mass distribution, which are supported on a set of positive measure. So the alternative way, so let me just focus first on Newton, so the spherical case, and then this will generalize to ellipsoids. So an alternative formulation of Newton's theorem can be done as follows. So essentially, you know that the Laplacian of UR is the surface measure on the ball, and then you can integrate this in R. Let's say you consider little u of capital R and rho to be the integral from R to rho of this family of potentials UR dr. So just average over an annulus. Then the Laplacian of u r rho is going to be the integral from R to rho of the Laplacian of UR. But this is the integral from R to rho of the surface measure. And this is just bipolar coordinates. This is simply the indicator function of the ball of radius rho minus the ball of radius r, right? So here the surface measure is normalized already to have not mass 1, but to have mass, rho square. In this way, you have now this function which has, you're putting uniform mass distribution in an annulus. And then if you look at the gradient of this function, UR rho, this is the integral from R to rho of the gradient of UR dr. And then this gradient is going to be 0 in the smaller ball. Okay, so if you have the one ball and the second ball, this is R and this is rho, and you take any shell in between, none of this shell will exercise inside BR any force. So of course, the integral of this will be 0. So this will be 0 in the smaller ball. So you have these functions which satisfy, they have constant gradient inside. So this means that they are constant inside the ball of radius R. So up to adding a constant, we can assume that UR rho is identically 0 in the smaller ball, BR. And so you see now you have this function which are 0 in the ball. They have Laplacian 1 in the annulus. But now you can just, these have bounded Laplacian uniformly in rho. So you can now let rho goes to infinity in this formulation. Even if the integral of would be infinite, like the integral of the charge, there is no problem here by compacting, you just let to infinity. And so as if you let rho to infinity, you will have what? You will have a function UR, which will be identically 0 in BR. And then Laplacian of UR will be equal to the indicator function of the complement of the ball, okay? So what are we saying? So we are saying that if you give me a ball, I can find a function which is 0 in the ball and satisfies Laplacian 1 outside. And in fact, because the Laplacian is bounded, the gradient also has to match there. The function will be C1 regular. These functions are uniformly C1, so you will detach with 0 gradient. So now you can give a definition, which is not the standard definition, but I chose this one for the purpose of the talk. I will say that omega is a null quadrature domain. And I will use the NQD. If there exists a function u from Rn into R, such that u is identically 0 in omega, and Laplacian of u is equal to the characteristic of omega complement. Okay, this is not the standard definition, but it's an equivalent definition of what people use for null quadratic domains. So this is just a way to generalize a bit Newton's theorem. So essentially, Newton's theorem you can formulate by saying that balls are NQDs, so they're null quadratic domains. Laplace Evo result will tell you that ellipsoids are NQDs. And then once you have ellipsoids, you can take limits of the ellipsoid. This formulation is kind of robust if you take limits of sets. So if you have a sequence of omega which are null quadratic domain, the sequence of functions u related to omega will also be will have compactness properties, and then you can pass to limits. And so by taking limits, you discover that also paraboloids are NQDs, because paraboloids can be seen as limit of ellipsoids if you center them properly and then you dilate them to infinity. And also you can do products, let's say cylinders over them, and plus cylinders over them. What do I mean? You can take, let's say, an ellipsoid of them in Rk cross R n minus k, or a paraboloid in Rk cross R n minus k. So you can multiply trivially by Rn minus k as many times you want. You get just a solution which is a set which is invariant in n minus k direction. And this will be also a null quadratic domain. Okay, so this is a list of possible null quadratic domains. Now my title talked about obstacle problem, and in fact there is a theorem. So it's contained in a paper by Caffarelli, Karp, Shagolian, and also the Karpa-Margulis. Essentially, it says that, let's say, U is a solution of this system. So U solution of U on omega identically 0 and Laplacian of U equal characteristic of omega complement. If and only if U non-negative and Laplacian of U equal characteristic of U positive. And well, and omega is the set U equals 0 in this definition. So you see in the formulation of null quadrature domain, there is no negativity assumption. But in fact, if you look at this potentials U that you generate, you can make them, you can in the end show that they're non-negative. And for these non-global solutions. So in fact, you can assume that your U is non-negative. And the omega coincides with the set where U is identically 0. Okay, so this is the connection between null quadrature domain on one side, and this is the obstacle problem on the other side. So of course, most of the people here in the audience are familiar with the obstacle problem, but maybe I will just spend 3 minutes just remind you why this is called the obstacle problem. What it is this? So a small parenthesis on the obstacle problem. The obstacle problem is the following. So usually you have some domain. Let's say I am in Rn. I have some domain D where I have functions defined on this domain. So let's say what I have is that over D, I will I imagine that I have some let's say metal wire here represented by the graph of some function f. So f is a function from the boundary of D from 0 plus infinity. So it's a positive function. And what I do, so I have this my metal wire, and I look at elastic membranes that are attached to this wire. Well, maybe the picture I did is not ideal. Let me do it a bit first. So I will have my elastic membranes that are attached, but what happens is that my elastic membrane, so this is V, let's say, and this is V equals 0, my elastic membrane is subject to gravity. So there is, what's happening is that I'm minimizing, so I look at minimizers of elastic energy, so 1/2 grad V square inside D, plus potential energy V in dx, with the constraint that V is non-negative, because you have to think that there is this table under my elastic membrane that prevents the membrane to go at negative values. So that's why it's called the obstacle problem. So there is this elastic membrane, gravity acting, but I cannot become negative because of this obstacle. And then if you write the Euler-Lagrange equation, then you discover that V is a minimizer, if and only if Laplacian of V equal the characteristic of V positive. And so you see that being a non-negative minimizer is exactly the system that I wrote before on the top, this Laplacian of U equal characteristic of U positive. Of course, if you have questions as I speak, and it's I don't know, if something is not clear, please feel free to ask, or I don't know, write in the chat. So this is just to explain you why it's called the obstacle problem, and you see that knowing about the null quadrature domains is equivalent to look at solution of the obstacle problem, define the whole space. So usually when you study the obstacle problem, you look it in a domain D with some boundary conditions. Oh, sorry, I didn't write it, but of course here V on the boundary is equal to F. So F prescribed Dirichlet boundary conditions. And usually this is what you look. So it's a local problem. And of course, global solutions are a very particular case. So they don't come as minimizers. Usually they come because you do perhaps some blow-up procedure or something. And the effect of understanding global solution to the obstacle problem has implications also on local solutions, because morally, if I take a local solution like V here, the minimizer, and I look at some very small scale, then I can do a dilation where the small scale becomes 1, and then my domain becomes huge, and it's almost a global solution. And then you can kind of use this information global solution to say something about local ones. So there are connections, but I will not emphasize this in this talk. So let's go back just to our connection. So we were interested in null quadratic domains. And just the message is that the fact that I can classify null quadratic domains is equivalent. Oh, sorry, yeah, not in the chat. Of course, there is a square missing in my, thanks. In my energy, of course, is Dirichlet energy squared, of course. Thank you. So the point is classifying these null quadratic domains is going to classify global solution to the obstacle problem. What about then, what is an extra advantage now? So a good remark that we can make, thanks to Caffarelli, that proved a lot of theorems about the obstacle problem, is that if omega is a null quadratic domain, then omega is convex. Because in reality, here what I'm saying is that U solution, global solution of the obstacle problem implies U convex, which implies the contact set U equals 0 is convex. Okay. Just maybe another warning, just to say that I cheated. I didn't want to. So to be precise, when you look on the literature, null quadratic domains are the complement of the domains I said. So usually null quadratic domains is the complement of an ellipsoid, is the complement of a paraboloid, and you always have to take complements. For the sake of the talk, I just thought let's call them the opposite, just so that it's easier to say. But technically, there is a complement in the definition. But of course, it doesn't matter. So this is a useful information. It means that we are trying to understand convex sets, and we ask ourselves, when are these sets null quadratic domains? So we have our list by now, which is given by what I told you. So I took the result of Newton, I took the result of Laplace and Ivory, and then I took limits. Then, roughly 90 years ago, people started to wonder, okay, is this list everything, or can I find something else? So in 1931, so let's say results on this classification problem. So in 1931, Dives studied the case n equal 3, and he assumed that so now we'll switch back and forth between global null quadratic domains and obstacle problem. So just think Laplacian of U is characteristic of U positive and U non-negative. Okay, so this is my setup now. Although of course people didn't talk about obstacle problem back then. So Dives in 31, he proved that if n is 2 and the contact set U equals 0 is bounded, then U equals 0 is an ellipsoid. Okay, so he proved that in dimension 3, all bounded sets which are null quadratic domain must be ellipsoids. Then 1981, Sakai considered the case n equal 2, and he proved that the set of null quadratic domains is equal to ellipsoids, paraboloids, cylinders over them, and nothing else. So he proved the full classification for null quadratic domains in dimension 2. Proof uses complex analysis. So it's very specific to the two-dimensional case. 5 years later, 1986, there have been 2 results. First, Di Benedetto and Friedman. They prove that if n is greater or equal than 3 and U equals 0 is bounded, And also u equals 0 is symmetric with respect to all the coordinate axes, so xi equals 0. So all the coordinates, let's say, all the hyperplanes. So there is full symmetry between xi minus xi for every I from 1 to n. Then u equals 0 is an ellipsoid. Okay. And then the same year, still 1986, Friedman and Sakai proved this result without symmetry. So they managed to remove the symmetry assumption. Okay. So if you put if you look at these theorems up to 86, what do we have? We have the full theorem in dimension 2. So all null quadrate domains are classified in dimension 2. There are just ellipsoid, paraboloids, and cylinders over them. And we have the full result in every dimension for bounded sets. So provided u equals 0, if u equals 0 is bounded, then it has to be an ellipsoid. Of course, this at the moment, this leaves completely open the unbounded case. So u equals 0 being unbounded. So I'm not sure about the history, so I wasn't present back then, you know. But from what I heard, in some sense, it was already around the conjecture that you know, the list should have been that one in every dimension. So the list of ellipsoid, paraboloids, and cylinders over them was the full list in every dimension. It was already in there in the 80s. The first moment where it's really written down as a conjecture, it's in 1992. So this is by Shagolian. So he made the conjecture that the set of null quadrate domains is in fact the set of ellipsoids, paraboloids, and cylinders over there. So essentially 30 years ago, it was, you know, written down. So as there has been no result on the unbounded case until roughly 2 years and almost 3 years ago. It was published beginning of 2020. So the first result on the non-compact case, so U unbounded, was by Eberle, Shagolian, and Weiss in 2020. And they proved conjecture is true if n greater or equal than 6. And finally, just very recently, with Eberle, myself, and Weiss, 2022, we proved that the conjecture is true if n is greater or equal than 3, which, you know, closes the story because thanks to Sakai, the case n equal 2 is done. Okay, so so this is the statement. And what I would like to do today in the essentially other half of the talk is to discuss our proof. So maybe some words before I start. One could be surprised about this n greater or equal than 6 in the previous result. They strongly use it. They use that, and I will try to comment briefly on that. They strongly use that in high dimension, there are some integrals that converge faster than in low dimension. And in some sense, you know, the higher the dimension, the easier it gets, and things get more and more complicated as you lower the dimension. When they did it, they kind of, I mean, I also spoke with them. I remember Georg Weiss gave a talk about this result here in Zurich in 2019. And they had the idea that probably by pushing a lot their strategy, they could get 4 and 5. So they had the feeling that, you know, 4 and 5 was within reach. But it was rather clear to them that the three-dimensional case was really out of reach. And in fact, the proof I will discuss today, which is our approach, is different from what they did. You will see that they just separate between n equal 3 and then greater or equal than 4. And in fact, with our method, n greater than 4 becomes rather easy, I will say. So once you get the right way, it just comes rather easily. And really a lot of work is to do the 3-dimensional case. That's really where all the difficulty comes. And that I will not be able to really go in all of them because they become really technical difficulties, but I will try to give you a sense of the differences. Okay, so that's just a word. So, so what do you have to do, right? So you start, so let's say strategy of proof, right? So we have our function, Laplacian of u equal characteristic of u positive, u non-negative, and we are in a Rn, and greater or equal than 3. So without loss of generality, we can assume that any partial derivative is not identically 0. Because what does it mean? If you had one partial derivative which is identically 0, it means that our function is fully invariant in one direction, which means that in reality, so otherwise, u is independent of, let's say, the direction E, which means that it factorizes as a function of one less variable. So it's independent, let's say, on the first variable, and then it only depends on the other n minus 1. But then you just reduce the dimension by 1, and you work in a n minus 1. Okay, so by just lowering the dimension, you can always assume that you are in the minimal dimension where u is never invariant in some direction. Okay, so otherwise you would have this, and you just work in a n minus 1. So you just lower the dimension. Okay, now once you have done this reduction, you can prove, so there is, this was contained in some papers by, for instance, Caffarelli, Karp, and Chagall, and there were a bunch of papers also that were doing other stuff, and among the things they did, they were also proving the important results about global solutions. And in fact, once you know that you are in such a situation and you assume, so we can also, so assuming now also that u equals 0 is unbounded, then you can prove that u is what we call an Xn monotone solution. That I will tell you what it is in 1 second. So an Xn monotone solution is the following. It's simply, so definition, u is an Xn monotone solution. It's just a name. I don't know. We had to come up with something to call it this. If you have the following situation that Laplacian of u is characteristic of u positive, your space factorizes Rn minus 1 and R. So this is the En direction, and these are the remaining direction. You define the contact set to be u equals 0, and then the contact set will be something here. So the contact set is contained in Xn greater or equal than 0. 0 belongs to the boundary of the contact set, so that touches the origin, let's say. Our function u is monotonically decreased, so dnu is less or equal than 0. So it's decreasing on the En direction. And u of Rx over R square, so as R goes to infinity, so at infinity, it behaves like a quadratic polynomial depending only on the n minus 1 dimensional variables orthogonal to En, where Q is a quadratic matrix in Rn minus 1, positive definite. Okay, so this is a particular class of solution. So it's a solution, you see, where the contact set is all contained in a half space. It's not the full half space, it's just contained, strictly contained. The solution is decreasing in the n direction. And then as you look at the behavior of u at infinity, you know by for instance, by Caffarelli, that it always behaves like a quadratic polynomial at infinity, but this quadratic polynomial depends only on the x prime variables. So there is no xn variable in this polynomial. And also the quadratic polynomial is non-degenerate, so is strictly positive. So all the eigenvalues are positive. So this is a symmetric matrix. Symmetric matrix in a Rn-1. And this is strictly positive definite in a Rn-1. Okay. So there is a reduction work that you have to do, but in a sense, it's just a fact that if you have a global solution, which has no directional invariance and is unbounded, then it's of this form. In our paper, we prove this fact. Actually, we give a rather, I would say, elementary proof of it. It's not, I mean, it's not trivial, but once you get the right idea, you can prove it in 1 page, roughly, 1.5 pages. So that every solution of that form must be of this structure, okay? So for the, maybe if I have time at the end, I can say some words of how you prove that if you are, so if, you know, as I said, if you are, there is no direction of independence plus U is unbounded, then you are of this form. But let's say this is not the new part. This was already known. So I prefer not to lose time now on this part. And I ask you just to believe this part. So we have this configuration. Now you have to work with such a function. Okay, what do we do? The first thing we do is, okay, let's try to make some educated guess of how you look like, right? So we know that, sorry, this is Laplacian of U positive. So, you know, we know that, what did I do? Yeah, yeah, Laplacian of U positive. So what do we know? We know that the Laplacian of U is 1 outside and U is 0 inside. But you know, you can always, the key point is that you can prove is that, so fact, if you take this polynomial here, that you get at infinity, you know that the Laplacian of P is identically 1, where P of x prime is the polynomial x prime qx prime. So, you know, if you do this blow down, so you look at the solution at infinity, because the Laplacian U is 1 more and more as you go to infinity, because there is less and less contact set, then in fact this polynomial in the limit has Laplacian identically 1. Okay, which means that if you look at U minus P, and you look at the Laplacian, this is minus the characteristic of the contact set. So all the Laplacian U minus P is in the contact set. Okay, so now the question is, okay, can I use this information to guess how U minus P looks like? Well, the first thing you would like to say is that, okay, if I have this, then perhaps, well, U minus P should be something like minus characteristic of C convolved with the green function of the Laplacian. This is green. That's not totally true, because you could have up to harmonic functions, right? But this would be some first guess you would like to say. But okay, then you say, okay, can I make something like this rigorous? And the problem here you will face is that this convolution in general doesn't make sense, in the sense that it doesn't converge a priori. And this is actually a reason why the restriction n greater or equal than 6 was helping Shagolian with Eberle and Weiss, because in dimension 6, they could prove in the end that this convolution converged. But in our case, we just do a definition. So we do a few things. So the step 1 that you need to prove is that the contact set C is contained in something which, let's say, is contained a ball of reduced R union some set which is almost a polynomial. So something like kappa xn to the 1 plus delta. So for every delta positive, let's say BR delta and kappa delta. So the step 1 you do is that, okay, to to start, you would like to do some convolution with green functions. You need to make sure that some integral converge. So the first step is you have to understand how this set C behaves at infinity, because then you have to make sure that the integral converge. The first thing you prove, what is the goal? The goal is to prove that the contact set is a paraboloid. That would be our final goal if you want to prove the theorem. So first, let's say, step is to say, okay, it's almost contained in a paraboloid up to an error delta. So this is not really the behavior of a parabola. It's slightly bigger, okay, at infinity. But okay, that's good enough if you want to make sure that things start to converge. Then thanks to this step one, you can define the following function. Vc of x will be the integral over the contact set of the green function of the Laplacian, so maybe Gn, the dimension, in x minus y, minus the green function on y. I will write in a second what this, right? Plus grad Gny times x dy, where Gn of z is the green function of the Laplacian, so this is Cn z to the 2 minus n, okay? So what have I done? I told you what I would like to do is to convolve the contact set with the green function. But if you check under this condition whether this integral makes sense, you will see that the convolution makes sense if you only have this decay assumption, or even if you know that you are a parabola and you try to convolve with the green function decays like z to the 2 minus n. And you cannot integrate it on something that behaves like a parabola, unless you're in dimension 6 and higher. Then the integral converge. But if you're in dimension lower than 6, so 3, 4, and 5, this will not make sense. So what do? You start to remove some diverging terms. So you take the green function, the convolution this will be, but then you subtract the green function as a function only on y, so this doesn't depend on x. And then you subtract also the gradient. So I'm doing like a Taylor expansion. I'm subtracting the 0 order term and the second order and the first order term. In this way, this function, you see that this function for fixed x, for x fixed, this function behaves, so all this expression here is bounded by what? By the Hessian of the green function times x squared. So this is going to be bounded by x squared constant over y for y large, y to the n. So at infinity for y large, this decays faster because I remove 2 terms. And now with this extra 2 powers, this integral will converge. So this makes sense. I can define this function now. Very good. And now what we prove as a lemma, once we prove that VC is well defined, we prove that actually U is equal to this VC plus our polynomial P of x prime. So we have an explicit expression of our solution as the polynomial plus this convolution of the green function on the contact set. And also this VC is really a correction in the sense that VC of x is bounded by constant 1 plus modulus of x to, I don't know, 7 over 4. It's just a number less than 2. So at infinity is, is subquadratic. It's a quantitative subquadratic. So it really, our solution is a quadratic polynomial plus some correction, which is subquadratic. Okay. And now from this, what you would like to do is to improve this first. So the next step, so step 2, will be remove the delta. So I told you that you have this inclusion with a delta. And now the question is, can I really prove that my contact set is contained in a parabola, not without an 1 plus delta error, right? So asymptotically, there is a parabola that contains my contact set. So this is what we do, proposition. The contact set is contained in a ball of radius r, union x prime square less or equal than kappa xn. So it means that you have so I just take a ball just because I don't care what happens in a compact set. So let's say I have a ball here, and then I have my parabola, and my contact set must be, I don't know, somewhere here. Well, sorry, it's convex, so it will be somewhere here. This is my C. Okay. So how do you prove this proposition? Here is the first moment where there will be a huge difference between the high dimension and low dimension. So for in particular, n equal 3, n equal 4. So the proof in n equal 4 is almost trivial because it's just a computation. You assume that n is greater or equal than 4. You know that VC of x, it's up to a constant, is the integral of 1 over x minus y to the n minus 2 minus 1 over y to the n minus 2 minus x dot y over y to the n. Sorry, minus, I lost the constant. N minus 2 x dot y over y to the n. Okay. And now you work using the inclusion that you already have. And in fact, you prove that this is bounded by constant. Let me use kappa as a constant because C is the contact set. 1 plus modulus of x. So you prove that this VC is bounded linearly from below. Okay. But this is true if n is greater or equal than 4. You do the computation, and if n is greater or equal than 4, you prove that the negative part of this integral cannot grow more than linear. And then you are done because you say, well, take x in the contact set. Then you know that 0 is equal to u of x because u vanishes on the contact set, but u is VC of x plus the polynomial p of x prime. And this is greater or equal. So the polynomial I told you is positive definite. It's strictly positive definite. So it's going to be a constant times x prime square minus kappa 1 plus norm of x. And this, you just do the algebra. This implies exactly that x prime square is bounded by constant 1 plus xn for a different constant, which is exactly the inclusion in a parabola. So for n equal 4, it's a short couple of pages computation, just couple of pages because you need to do this computation here on the top. But it's nothing difficult. You just have to be careful. What is super difficult, and that's taken us, I would say, roughly 2.5 years, is to prove this result in dimension 3. So this is in dimension 3. It doesn't work at all if you just try any brute force or whatever. You will have logarithmic corrections all the time, and then you're lost. I mean, there is no log you can pay here. You really need the proof, and if you look at the paper, that's like a 6-page argument, which is kind of tricky. I would say I wouldn't find an obvious way how to. I don't know, you prove everything you think in your life and you keep going, and at some moment the right idea comes in, but until you go to the end, you don't even know that the idea is going to work, I would say. On that proof, I will not, let's say, it's very delicate. I mean, I don't have the time now to enter. I could give some intuitions, but I don't know, it will take a lot of time and it's not the point. So let's say n equal 3, true, but very hard. Okay, now this is not the only difference. We are not done. So now the key point is that if you're in dimension n greater or equal than 4, now we'll try to conclude the proof for n greater or equal than 4. You will see it comes very nicely. You can write your VC of x as the integral over the contact set. So up to a constant is 1 over x minus y to the n minus 2 minus 1 over y to the n minus 2 minus n minus 2 x dot the integral over the contact set over y to the n. So what you can do in dimension 4 is, you see, I have my integral, I split it as sum of 2 integrals, okay? I just decompose the integral. And the key point is that this is convergent. Okay, this integral in the convergence in dimension 4 and higher, which means that this is just a vector. This integral of y over y to the n over the contact set, it's a vector of some vector, which makes sense. And so then you have this extra term, WC. And what we prove is that, so you decompose it. So this term is linear. It's just x times a vector. So it's linear in x. And this WC of x, it's sublinear. We prove that in every, let's say in L1, the integral of WC over the ball of radius r goes like r to the 1/2. So it's sublinear. doesn't grow. Right. So what is the point? So what we have done now is that in dimension 4 and higher, u of x can be written as a polynomial px prime plus a linear term ax plus wc of x, which is sublinear, let's say little of x. And now what we do is that we build a paraboloid P such that the solution, the corresponding solution, so Laplacian of UP equal characteristic of P complement, satisfies that UP of x is P of x prime plus A dot x plus little of x. So we can build a paraboloid which has exactly the same second order term and the same first order term. Okay, so we can find a solution which has parabola as a contact set, but it matches our solution at the two leading orders. Now the question is how many parameters I need to do that. So in a paraboloid you can do the following. How you build a paraboloid? A paraboloid, you can think of it as, so you have your paraboloid P, which will be something like this, let's say, if you try to do extra dimension. So there will be a section here, right? So this is P intersection xn equal 1. So this is an ellipsoid, if you cut a paraboloid with xn equal 1. This object, the shape of this, so the shape of this is what is linked to the polynomial P here. So for each, once you tell me what is the polynomial here, there exists a unique shape which generates that polynomial. Okay, so that's how I fix the second order term, by choosing the shape of the polynomial when I intersect with the xn equal 1. But I still have a degree of freedom because the shape, this is just the shape, but doesn't matter the size. So if UP of x is equal to px prime plus little of x squared, so the dominant, if this polynomial generates this, if this paraboloid generates this polynomial, also u of gamma p of x is equal to p of x prime plus O of x squared. So you can take your parabola and dilate it, and this will not change the quadratic polynomial. Okay, so it means that I have a parameter gamma that is 3. What does this gamma will determine? Gamma will be used to match an. Remember that I have a vector here on the top. So A is a vector of the form A prime an. This is in Rn-1, this is in R. And the gamma is used to match an. So the dilation will match my n. Now I need to match A prime, still n-1 parameter. How do I do it? By translating my polynomial. So my polynomial will be something maybe not centered at the origin, will be translated by some tau prime, and then tau prime used to match A prime, okay? But then you see that there is still one parameter missing. I haven't used the translations in this direction. I can still take my parabola and translate it in the en direction, and this translation is for free. So what I'm saying is that, so once I construct my parabola, this paraboloid P, then u of P plus sigma n, so if I translate the polynomial in the n direction of x, will be equal to P of x prime plus A dot x plus little o of x for every sigma. So in fact, I have one parameter family of paraboloids that match my solution. And now, okay, now what I would like to say is that there exists one sigma for which this solution is equal to my solution. And then I'm done, because I will prove that my solution has a contact set which is a paraboloid, which is what I wanted. And then here comes the other idea of, I would say, of the paper, which is that we look at the ACF functional, Alka-Freire-Friedman functional. So the function is phi of r of u minus u p plus sigma n, which is, for people familiar, this is 1 over r to the 4 integral over br 1 over x n minus 2 grad of u minus u p plus sigma n positive part square times integral br of 1 over x n minus 2 grad of u minus u p plus sigma en negative part square. So we look at the Alka-Freire-Friedman functional applied to the difference of these two solutions. And the key fact is that this functional phi as a function of r is increasing. Not surprising, but it hasn't been used so much in this context. So a posteriori is not surprising, but to be honest, I haven't seen it used that much for different of these two solutions of the Husserl problem. But the key point is that because you see the two solutions match up to linear term, at infinity, my two solutions are sublinear, okay? So I know that this term, this function is a little o of x, and this function is a little o of x at infinity. But then, you have a little o of x function, you take the gradient, this is gonna be a little o of 1. And then you look at the homogeneity of this. This is like now an r square. This is an r square. And then there is an r to the 4. This cancels out. This is a little o of 1 at infinity. So this is a monotone function that tends to infinity, that tends to 0 at infinity. So it has to be identically 0 because it's increasing, it's non-negative, and it's 0 at infinity. So this means that phi of r is identically 0, which means that the integrand must be identically 0, which means that in fact, either the positive part or the negative part is identically 0, which means that either u is greater or equal than u of p plus sigma n, or u is less or equal than u plus sigma n for every sigma. And now you just take sigma very, very large, and you prove that there is one case where for sigma very large, one inequality is true. For sigma very, very negative, the opposite inequality must be true, because these are two parabolas. So you're taking a parabola and you're sliding it up and down, and you have your fixed set. So it cannot be that your set is going to contain all the time a paraboloid, no matter how I translate it up and down to minus infinity. So at some moment, there is one inclusion. At some moment, there is the opposite inclusion. By continuity, there is a moment where they must be the same. That's the only option. And so this is how you conclude. In dimension 4. So this is the easy case, okay? I think I'm running out of time. So, but maybe if you give me 5 extra minutes, I will just try to tell you why n equal 3 is completely different. Also because I started 5 minutes late.
Yeah, of course, that's fine.
So for n equal 3, the real problem is that everything I said on this case, it fails, because if you take, so what is the key idea here is to write your expansion as a linear term. You see, it's a linear, I wrote VC as a linear term plus a sublinear term. And then you are done because you match the linear term. The problem is that for n equal 3, if you look at the size of your VR, of your potential VC, this goes like R log R. So there is no way this can match an affine function. There is no affine function whatsoever in the expansion. So you cannot say that the VC in dimension 3 is affine plus sublinear, okay? Because otherwise this will grow linearly at infinity as R. So what we prove, here we have to do many things. So the step 1 is to prove that as type of PMO type estimate, we prove that for every R, there exists an affine function AR such that the average over BR of VC minus AR is bounded by constant. So you can prove that your function is linearly close to a affine function, but the affine function changes from scale to scale. And then what do you do? The step 2, once you have this affine function, so for every R, you build a polynomial a paraboloid PR such that the solution corresponding to it, UPR, will be equal to Px prime plus this affine function plus little o of x. This you can do like in dimension 4. But what is this function doing? This is only matching your solution at scale R for a function that changes. Okay, then what we do, we consider U infinity to be, so let's say U of P infinity to be the limit, is the limit as R tends to infinity of UPR. Okay, this is still not enough at all, because what you're doing, you're just matching linearly your solution on larger scales, which is like saying that this paraboloid that I built is matching my solution at infinity. But there is no moment where it really matches. It's just that infinity is matching, because I'm getting this affine, it's matching this affine function in the limit, which is the best affine function I could find. Okay, so this is still not enough. What we prove now? What we prove, and the proposition is that, okay, now if we consider our solution, so we consider W of x to be a blowdown of our solution minus UP infinity. So some limit as R tends to infinity of U of Rx minus UP infinity of Rx over R, a linear blowdown. We prove that this exists up to subsequences. So at infinity, we think, okay, our functions are almost matching, but it's not true. We couldn't really match. We match only up to linear error. So that's what we have, right? Like almost linear matching. But now we do a blowdown and we look what's happening at infinity. And then what we prove is that either W greater or equal than 0 or W less or equal than 0, or W is linear. So W of x is of the form B dot x. So at infinity, the difference of our solution minus these paraboloids is behaving like an affine function, or it has a sign. Now, if it has a sign here, you are happy, because here you can apply Alcafarelli-Friedman again, and because it has a sign at infinity, you prove that at infinity, so in this case, you prove again that the energy at infinity will be identically 0. So if you're in case 1, in reality, you conclude as before, because you realize that in reality, the energy at infinity had to be 0. The problem is when you are affine at infinity, after you do this blowdown. And so I'm done, really. So the philosophy is that if you are in this case, what does it mean philosophically? It means that, so if you are in this case, it means that for R large, U minus U of P infinity in large balls, like say in some large ball BL, looks like linear, like B dot x. Okay, so on a large scale, in a very large ball, I'm almost linear. I look like that. And then I would like to say, okay, but then perhaps I know how to correct linear functions on paraboloids. I can dilate stuff so to compensate for this linear function. So what we prove is that there exists lambda k, let's say lambda r, and translation tau r, such that U minus U lambda r P infinity plus tau r looks in BR, looks like 0, where tau r is bounded and lambda r is minus 1 goes to 0. So this is a bit the magical part. So what you say is that, okay, I look at infinity, then I perturb slice my paraboloids, and then I can almost cancel this linear function. And I can do it with infinite. The miracle is probably this, is that you don't need, this is miracle of dimension 3, you don't need really to change this much the opening of the parabola. You just need a little of 1 in the opening of the parabola. It's not that you have a parabola and you have to double it. You remember I told you in dimension 4, to changing the opening changes the linear function. But in dimension 3, there are logarithmic corrections. And now the logarithmic correction go in your favor. It like tells you that you can just change it very, very slightly, and you can cancel linear terms. So you are able to compensate. And then in the limit, when you let everything goes to 0, this lambda r will go to 1, tau prime will go to, this will go to some tau prime. And then you discover that in the limit, the Alka-Farelli-Friedman energy, you use again that is monotone, blah, blah, blah. The energy of u minus u of p infinity plus tau prime, so you have to do a small translation, will be tending to 0 as r goes to infinity, which means that you are ordered. And in fact, once it is true, you also prove that this energy also goes to 0 if you translate in the en direction. So translation in the en direction always for free, which means that u is either greater or equal than u of p infinity plus tau prime plus sigma n for every sigma. And then as in dimension 4, you conclude. So it's a bit involved. I don't know. I don't have an easy way to explain that, right? But it's really, you pass to the limit first. You have to do 3 passages to the limit. First, you match on the scale BR, and you find a limit at the very large scale. Then you do a blowdown, and you prove using again the Alka-Farelli-Friedman formula that blowdown is linear, and then you recompensate on the p infinity to get then this planet, this 0 energy at infinity for Alka-Farelli-Friedman. It's a bit up and down. So you see, dimension 3 is really much more difficult. So I think I'm completely out of time, so I will stop here. Thank you very much for the attention.
Oh, thanks, Alessio, for the very nice talk. We've got time for questions now, so if someone has a question, please feel free to ask.
Yeah, I have a question. Alessio, can this method also be used to cover the 2D case?
I don't think so. I didn't think, we didn't try at all, but I would say that the 2D, so here you see there is this R log R behavior that you get after the polynomial. So let's say after you subtract the quadratic term, you get an R log R. If you are in dimension 2, it's R to the 3 over 2. So here you will get R to the 3 over 2 as a behavior.
Okay.
And then you really need to subtract different things. So I haven't thought at all, but let's say the way it's built, it's really like borderline in dimension 3. The 2D case is a different approach. Although I must say, to be honest, I didn't spend much time to think about it. But I don't see an obvious way, let's say, right? So it's like the 2D case from this approach looks more and more difficult, even more than this one. But it's true that there is a completely different trick to do that. But I haven't thought about it, but I don't see a direct way to do that. One thing I could comment is that this method gives you a very short proof of the compact case. So we remarked this in the paper. If you use this approach, expanding with this VC Alka-Farelli-Friedman, you get the result for the compact case very, very quickly, because essentially every integral converges. When C is compact, there is no problem of convergence of integrals, and then actually you conclude very quickly in every dimension. So it's I don't know, even in so dimension 2 also will work there, because then it doesn't matter anymore. There is no divergence of integrals. Then it's much easier, very, very easy.
Okay, thank you.
Hey, Alessio, I have a quick question. So, you use a lot of monotonicity formula of Alka-Farelli-Friedman. Do you think there's a different way to quantify it? Because you are, I don't know. I mean, you are using a lot of information at infinity. Is there
I mean, the problem is this, right? So if you look at dimension 4, that's why I did it first. In reality, I use very little, I use very little. I use the fact that once you know that you have 2 solutions of the obstacle problem that match at infinity sublinearly, then they must be equal. That's essentially what we prove. And this is a consequence of Alka-Farelli-Friedman. And I don't have another way to do it easily. Although it's true that the paper of Figalli and Weiss and Eberle was not using ACF, so they were really doing more by hand. They were able to match, but they couldn't do it with sublinear. So that the difficulty is that once you accept Alka-Farelli-Friedman, little of X is enough to conclude. For them, they really had to go to the next door, They had to go up to constants before they could say that the two solutions were the same. And that was why they needed a lot of work, and they could not do it in dimension below 6. So in reality, in dimension 4, we just use it once. We just use that if the energy is 0 at infinity, then it's 0 all the way. So it's not that we use a lot. It's in dimension 3 that we have to use it first to do the blow up, then the blow down, and then another blow up. So it's really in the 3-dimensional case that we use it all the time. But I don't know. I mean, when we realized that we had this tool, actually, we got very excited because then we realized quickly how to do dimension 4. But then we were struggling for a lot of time still, even with that, because of the three-dimensional case. We didn't understand how to avoid this R log R divergence. We didn't know what to match for a long time. That was our difficulty.
Thank you.
Any more questions from the audience? It seems no, so let's thank Alessio again.
Thank you.
Thank you.
Thank you very much for listening.
Yeah, thanks for this very nice talk.
It was clear.
Very nice.
Thank you. Yeah, I went maybe a bit fast towards the end, but I hope at least up to dimension 4, I hope it was clear. And then the 3, yeah, it's a bit involved.
Oh, it was nice. I liked seeing you.